Alright, we're going to be talking about the mean value theorem for definite integrals. And so I've got the theorem stated here as the mean value theorem. We've got f of x is continuous, which is really important, this thing about being continuous in a lot of our theorems. On the closed interval AB, then there's at least one number c that exists in the open interval AB such that, and so we've got the integral from a to b of f of x dx is equal to f of c and b minus a. So let's put a picture to this so you get a better idea of what in the world we're talking about. So here's our function f of x, and remember we're on the closed interval between 1 and 3 here, so it says that we have some f of c that's between f of 3 and f of 2 here, and there's at least one c between this interval here. Okay, there's at least one c, right, that'll give us f of c, and f of c will be between f of 3 and f of 2. Now this is really interesting geometrically. Let's take a look at it. So I've got this picture here. Now remember, we were taking the integral of the function between 1 and 4, and we're kind of finding the area of this function right here. Now what's interesting is there's some number between 1 and 4, okay, here on the x-axis, that when we plug it into the function, alright, we get f of square root of 7. But if we took f of square root of 7, which happens to be the height here of this purple line, and we multiplied it times the difference between 4 and 1, we would get the area of this rectangle here. And it turns out that the area of this rectangle, okay, that I've got drawn here, is equal to the actual area under the curve. The area under the curve. So both of these are equal. So there is some c such that, in other words, there's some point here on the graph. Okay. Now I'm not saying that this particular picture here, I'm not even sure this is to scale. I don't know. Maybe it is. But actually it is to scale, because I did graph this on a graphing calculator, and I do know that the square root of 7, or f of square root of 7, that point is actually right here on the graph. So I'd have to say this picture is pretty true. But anyway, that this area here is equal to the area of the rectangle. I think I might have already said that. But what's interesting is there's some point on the graph, some point, right, that we can draw out a rectangle and then get the area of up underneath this curve here. But this is the mean value theorem, and mean means average, more or less. And anyway, so all right, let's go down and look at the math here. I'm getting all caught up in nothing. All right, so back in the theorem, this is what it was saying here. So we want to find the c such that. So we've set it up here. So the idea here is, how do you find c? Well, we've set it up, okay, just like what the theorem says. All right. How did I get the 1/3 over here? Well, I took the 4 minus 1. I got 3. Divided both sides by 1, or multiplied both sides by 1/3 to get rid of the 3 over here. And so now we're here. Take c, plug it into the function, and of course it was just x squared, so you end up getting c squared. And now we're at this point. So we calculate the integral over here. Right, x to the 3rd over 3, got the 1/3 out here. We're going from 4 to 1, so we do our calculations, plugging in the upper limit minus the lower limit, simplify it down, and we get 7. And then of course we square root both sides, getting c is equal to the square root of 7. So that's what I've got labeled here on the x-axis is our square root of 7. So anyway, this is just an application here of the mean value theorem and how you solve for c.